Hi, my name's Gabe. For this problem, we're asked to find the area of the region bounded by the graph of 2 minus x squared on the interval from -1 to 1. And we want to do this by using the limit process. So we really want to think about taking this interval and we want to break it up into n regions so that we can come up with n rectangles to start finding the area. So let's go ahead and let's actually start thinking about using rectangles to find this area under the curve. All right, so since we're using rectangles, we want to think about, well, the width of the rectangles and the height of the rectangles. So let's start by thinking about the width. So we want to break this region up into n rectangles. So we want to break this interval up into n smaller intervals. So the width of each of our rectangles is going to be given by the length of this interval, which is going to be 1 minus -1, divided by n. So what this means is that the width of each of our rectangles is going to be 2 divided by n. Now we also want to think about, well, what should the height of each of our rectangles be? So since we're using n rectangles and the height is going to be different depending on where we select these rectangles, we want to think about using I to maybe index which rectangle we're talking about. So we'll think about letting I equals 1 give us the height of the first rectangle, I equals 2 give us the height of the second, all the way up through I equals n giving us the height of the nth rectangle. So if we're talking about the height of these rectangles, well, we want to go back and look at our function. And like I said, we're not just looking at our function evaluated at one point, but we're evaluating it at a bunch of points to get a lot of heights for our rectangles. So we're going to start at -1, and what we're going to do is we're going to keep adding this 2 divided by n. And since we're using I to index it, well, we want to add 2 divided by n times I. So this is the height of all of our rectangles, and let's spend a little bit of time writing this out and simplifying just a little bit. So for the sake of space, I'm going to come right underneath it. And I just want to plug -1 plus 2 divided by n times I into our function. So this is going to be 2 minus -1 plus 2 divided by n times I, this quantity squared. And again, we can go right from here into writing down the formula for the area using limits, but let's take another minute or two just to simplify this before. So this is going to be 2. We can expand this. So we'll be subtracting. We'll have 1 minus 4 divided by n times I. And finally, we'll be adding 4 divided by n squared times I squared. And again, we can keep simplifying. So we have 2 minus 1 will be 1, and we'll distribute this negative sign, so we'll be adding 4 divided by n times I, and we'll be subtracting a 4 divided by n squared times I squared. So here we have the height of all of our rectangles, and we also have the width of our rectangles. So now we can go ahead and write out the area. So the area is going to be given by a limit. So we'll be looking for the limit as these number of rectangles, n, approaches infinity. And we'll be summing all the areas of all of these rectangles that we were looking at. So it's going to be the sum from I equals 1, the first rectangle, up to the nth rectangle. Now, the heights of all of our rectangles were given to us down here. So 1 plus 4 divided by n times I, minus 4 divided by n squared times I squared. And now we'll want to multiply this, the heights of each of our rectangles, by the width of our rectangles, which is just 2 divided by n. And here, we're going to do some algebra and just simplify this. So the area is still going to be equal to the limit as n approaches infinity of the sum from I equals 1 to n. Here we can go ahead and think about distributing this 2 over n. So we have a 2 over n plus an 8 over n squared times I minus an 8 divided by n cubed times I squared. Now we can use the properties of summations to go ahead and rewrite this. So let's just leave this limit as n approaches infinity out front. And I'm going to put a parenthesis here since we're going to be breaking this sum up. So let's just look at this sum from I equals 1 to n of 2 over n. Since 2 over n doesn't have an I in it, we can think about it almost as being a constant when we're talking about the summation. So we can pull this 2 over n out in front of the summation, and we can write this as 2 over n times the sum from I equals 1 to n of just 1. So that's what just this piece here becomes. Next, we'll talk about this 8 divided by n squared times I. Similar to this 2 over n, this 8 divided by n squared, we can also think about that as being a constant. So we can pull that out in front of the summation symbol. So we'll be adding an 8 divided by an n squared. Notice we can't pull the I out in front of the summation symbol because we're summing with index I. And finally, looking at this 8 divided by n cubed times I squared, it'll be similar to the previous two, where this 8 divided by n cubed can be treated as a constant. And since the index of the summation is I, well, we have to leave that after the summation symbol. So we can think about this as a negative 8 divided by n cubed. And we have our summation from I equals 1 to n of I squared. Now here, we'll go ahead and use the properties of these summations to rewrite each of these so that we don't have to deal with summations. So this is equal to the limit as n approaches infinity times, well, here we have a 2 over n, and the sum from I equals 1 to n of just 1 is n. So what we'll see here is these n's will cancel. Plus, we have an 8 divided by n squared times the sum from I equals 1 to n of just I. Well, the sum from I equals 1 to n of I is n times n plus 1, all divided by 2. So here, we can also do a little bit of simplification. So we can cancel this n with one of these n's, and we can rewrite this 8 divided by 2 as just a 4. And moving along, we're subtracting an 8 divided by n cubed times the sum. And we know that the sum from I equals 1 to n of I squared is n times n plus 1 times 2n plus 1, all divided by 6. So here, we can also do a little bit of simplification. So we can cancel this n with one of these n's. And since we have an 8 divided by 6, we can write that as a 4/3. So now what we want to start thinking about, well, in here, we want to try to get a common denominator so that we can eventually take this limit. Because if we try to take this limit now, it'll sort of be a little messy. So, like I said, let's try to simplify just a little bit. So just by looking at the denominators, we see that the least common denominator would be a 3n squared. So let's go ahead and let's multiply and divide each of our terms so that we can get a common denominator of 3n squared. So here we just have a 2, so we're going to multiply the numerator and denominator by a 3n squared. So this will give us a 6n squared divided by a 3n squared. Moving along here, we're going to multiply the numerator and denominator by a 3n, since the denominator here is just n. So that'll leave us with a 12n times n plus 1, since we multiplied the numerator by a 3n, and we're multiplying the denominator by a 3n also, which will leave us with a 3n squared. And over here, well, the denominator is already a 3n squared, so we'll just be subtracting a 4 times n plus 1 times 2n plus 1, all divided by a 3n squared. Okay, so now we have this figured out. Well, let's go ahead and let's simplify each of these numerators. So this is the limit as n approaches infinity. Let's also, at the same time, maybe combine all these terms. So we'll have a 6n squared plus, here we'll have a 12n squared plus a 12n and here, let's actually go ahead and we'll multiply this out. So we'll be subtracting a 4 times, well, we'll have n times 2n, which will be 2n squared. Here we'll have plus n plus 2n, so we'll have a plus 3n, and then finally just a plus 1. And this is all divided by 3n squared. So finally, we can combine some terms up in this numerator, and we can finally get this down simplified pretty nice. So let's go ahead and do that. So what we're left with is the limit as n approaches infinity. Well, we have a 6n squared plus 12n squared, so that's going to be 18n squared, and we'll be subtracting an 8n squared, so that leaves us with a 10n squared. Now we have a 12n, and we're subtracting a 4 times 3n, so we're subtracting 12n, so that leaves us with 0n. And finally, we have a minus 4 times 1, so we're subtracting 4. So the numerator simplifies to 10n squared minus 4, and the denominator is still 3n squared. So here, we can go ahead and use our properties of limits to actually evaluate this limit. So since the degree of the numerator is equal to the degree of the denominator, they're both equal to 2, we know that this limit is just going to be the ratio of the leading coefficient of the numerator to the leading coefficient of the denominator, which in this case is going to be 10 divided by 3. So what this tells us is that the area of the region bounded by 2 minus x squared on the interval from -1 to 1 is 10/3. Thank you.